Okay, welcome to the second session of the QBF workshop. Yes.
Button.
Okay, thank you. Okay, so welcome to the second session of the QBF workshop. We will continue with two talks. Our first speaker is Friedrich, and he will talk about certified circuit reconstruction for QBFs. Please.
Yes, this is work in progress with my remote master student, Alex Weng. Oh yeah, okay. So this is something that I talked about in the tutorial. We often use premix conjunctive normal form as an input format for QBF solvers. But over the years, it has turned out that maybe that's not always a great idea. And there are a couple of reasons for this. So this is the default format. If you run solvers and you look at what they do, I'm thinking specifically quantified CDCL solvers, then on many instances, you'll see that they end up generating many large cubes. So remember, in quantified CDCL, you not only learn clauses which constrain the existentially quantified variables, you also learn terms or cubes that constrain the universally quantified variables. And if you start out with no constraints on the universally quantified variables, no cubes, then it takes a lot of time for the solver to generate these constraints one by one. And the constraints that it generates end up being very large. So this is a bit anecdotal, but if you look at the log of a solver while it's running, there are instances where it just keeps generating terms and doesn't seem to get anywhere. Now, actually, Mina, I think, is going to give a talk right after that looks at this from a proof theoretic perspective. Even early on in, I think around 2005, people noticed that even though there is a natural correspondence between two-player games and quantified Boolean formulas, it's not easy or natural to encode games in premix conjunctive normal form, because while you can easily express that the existential player has to obey certain constraints, it's not easy in CNF to express that the universal player has to obey certain constraints. So there's this paper, even in 2005, that suggests that premix conjunctive normal form maybe is not a great input format for QBF solvers in general. And what is surprising is that even if you have a premix conjunctive normal form QBF that you're starting from, it can give you a speed up if you perform what I would call a trivial conversion of this into a circuit and then generating a DNF representation from that, generating cubes from that. What I mean by this is that given a CNF matrix containing, let's say, M clauses, would introduce M universally quantified variables, one for each clause, and add terms saying that you may, so for each of these clauses, and every literal in a clause, whenever the literal is true, in which case in this cube would vanish, right? Then the universal player has to set the variable associated with that clause to true, right? So one has to kind of invert the reasoning a little bit here. For the universal player to not satisfy this term, they have to set vi to true, in which case this literal becomes false, right? So you add all of these terms requiring that you can only set these vi variables to false if the corresponding clause is not satisfied. And then you also add one large term that says the DNF is true if all variables are set to true, right? And so that's a DNF translation of your CNF that uses M new auxiliary variables. And it's a very, it's a trivial thing. You don't really have a circuit structure here, but even in that case, sometimes you can get short refutation, or short proofs of true QBFs using this, or exponentially shorter proofs of QBFs using this conversion, then deriving compared to using the trivial DNF conversion that's performed by the solver that just enumerates satisfying, that just discovers satisfying assignments and cubes one by one. But what we can often do is really reconstruct a circuit representation from Preenix conjunctive normal form. We have some Preenix conjunctive normal form QBF, give that to circuit reconstruction, and then obtain a Preenix normal form QBF in this QCIR format. There are, I would say, two kinds of circuit reconstruction. There's what I call syntactic circuit reconstruction, where you look at the CNF and you try to discover patterns, clause patterns corresponding to clauses introduced by Zeitin conversion. So if you look at these three clauses here, then you can think of this, or you can, this would correspond to the clauses that get introduced when you have an AND gate with X and Y as inputs, where Z is the Zeitin variable, right? And so syntactic gate detection tries to find these clauses and then replace the Zeitin variables with the original gates, or the gates that they define. There is a paper on that, or on using that in QBF solving from about 10 years ago. And then more recently, there was a paper that uses this kind of gate detection to allow for shifting variables around in the quantifier prefix to make formulas easier to solve. Then there's what I would call semantic gate detection, where you use a SAT solver and sometimes interpolation from SAT proofs to figure out whether certain variables are defined by other variables, and then extracting the definitions, replacing the variables by the circuits that express their definitions. I did this in 2020. There's another paper where this is used for SAT in a more simplified setting, or this is, I think this is a thesis on this. Then Armin and Matthias Fleury also have a version of this tailored to SAT, where they have I think a small SAT solver inside the larger SAT solver that they use to detect definitions. Okay, let me briefly explain how quantified CDCL can use circuit reconstruction. Start from this Preenix conjunctive normal form QBF, give it to circuit reconstruction, and then you get this QCR formula. And then you use Zeithin transformation, kind of the opposite of circuit reconstruction, to obtain, on the one hand, a Phoenix conjunctive normal form translation of your circuit. Give that to the QCDCL solver. And you also, oops. Okay, please remember to consume enough cumin seeds. So we apply the dual of Zeithin transformation to derive a DNF that's equivalent to the circuit, and that we can use to initialize the cube database of the solver. And this is something that Martina and Alexandra Gutieva, I think, figured out that that's actually a good idea to combine circuit reconstruction with CDCL style solving. Okay, so for instance, if this is our initial formula, this is a bit of a silly example, but bear with me. I think the underlying idea can be illustrated with this. Here we may discover that X actually corresponds to, or X is a Zeithin variable that comes from an AND gate with inputs U and E. So we would reconstruct this this circuit, which actually is also in CNF, but in general, this would be a circuit that's not in CNF. And then we would want to, again, take this circuit and convert to CNF and DNF. Okay, so CNF transformation, let's say, is this. Again, assume this is a more complicated circuit where we really need to do this. And then we can transform to DNF like this. Now, in this example, this original PCNF and the PCNF we generate by Zeithin transformation after the circuit reconstruction are exactly the same. But even in that case, it's worth doing that, or it may be worth doing that, because we get the DNF as well, right? And the DNF can help the solver find a proof, even if the refutation proof size doesn't really change. Again, Mina will talk about this in some sense in the next talk. Okay, in general, of course, if you use semantic gate extraction using this definition mining, then the Zeithinized circuit will be different from the original Phoenix conjunctive normal form QBF. Okay, so that's the way quantified CDCL can use circuit reconstruction. And now the idea of or what we wanted to do in this work was to obtain proofs for the original Phoenix conjunctive normal form QBF when we use circuit reconstruction. And here's the basic idea. We only do this for the moment, only do this for false formulas. So that's a restriction of this approach currently. And we take so the first part of the refutation will be just the refutation of this Zeithin translated circuit generated by the QCDCL solver. Right? So the QCDCL solver will generate a Q resolution proof, a Q resolution refutation of this formula. And we can then turn that into a refutation in a different proof system called QRET. This is a refutation of this result of applying Zeithin transformation to the reconstructed circuit. That's one part. And now we need to sort of relate that refutation to the original PCNF QBF. And for that, we want to, or so far we want to treat the circuit reconstruction algorithm as more or less a black box. The requirements we have I'll explain shortly, but in order to make things easier for us, we'll just use a SAT solver to derive a part of the proof that we need. So we'll use the again this Zeithin translated circuit the CNF version of it, and the original matrix to generate a proof of, well, of a propositional proof now of the matrix of the formula from Titan translation from the original matrix. Just a propositional proof here. And then what we want to do is just take this initial, well, or take this proof P that derives the clauses in this formula from the original matrix and append the QRAT refutation. And thereby obtain a QRAT refutation of the original PCNF formula. Now, actually one thing that preparing the slides I realized is that, or I'm not completely sure whether every RAT refutation is in fact a QRAT refutation. I think it's not a trivially true statement, but maybe Martina can help me figure that out later. So far, at least the checker has accepted the RAT, or really RUP, reverse unit propagation proofs, but just formally, I'm not sure whether we should expect that happening for every instance. Okay, so a bit more specifics about this, about how to obtain that RAT proof. So we start again from the PCNF QBF, obtain a circuit, quantified circuit by circuit reconstruction. Say this is the circuit we get, and then we apply Titan transformation to obtain this again a CNF formula that we use to initialize the clause database of our solver with. So let's say we introduce these Titan variables in our translation. Here's the full translation. So it's just the gate, well, the definitions of these variables plus a unit clause saying that the output has to be true. And we generally introduce these auxiliary variables at the innermost level. Okay, now, there should be an animation here. What we want to do now first in our RAT refutation is introduce the clauses coming from Titan translation for each gate in topological order. So we start here with the gate with the definition of Z1. And that clause will be RAT on Z1 because that variable so far does not occur in the formula at all. We can add this clause, and then we can take the other two clauses which contain not Z1. And these will be, so the only clause in which Z1 occurs so far is this one. So so we only need to look at resolvents for the RAT property of this clause with this one. And that will be a tautological clause because it contains both U and not U. Again, so this is for RAT. For QRAT, maybe one needs to look into this a bit more, in a bit more detail. So this is why we can introduce these clauses in a RAT proof. They contain a variable that's not part of the CNF so far. And we can do that in following the some topological ordering of the proof from the input to the output, introducing all these definitions. So that part is, in some sense, trivially a RAT proof. And then for what remains to add is this unit clause here, right? So never mind this comment at the top. I'll talk about this in a moment. What we need, so the last part is adding this unit clause, and for that we use a SAT solver. So what we want to get is a a refutation of the propositional matrix here, the gate definitions, and the negated output gate. So what we want to say is that if these clauses are satisfied and I have these gate definitions, then the output gate has to be true. Okay. We're kind of saying whenever we have a satisfying assignment of our original matrix, and these gate definitions apply, then the circuit would have to be true as well. I have to admit I haven't thought in detail about which kinds of or which circuit reconstruction techniques this works for. I think, well, I mean, certainly it should work for Zeitling transformation, because if you if you just take your CNF and it's a, that CNF is obtained, the PCNF is obtained by Zeitling transformation, and take a satisfying assignment of that, then there's just a projection of that onto the input variables of your circuit. That should be a satisfying assignment of the circuit, certainly. I think this also should work for Plysted-Greenbaum and for plugging in definitions that you find in the at the CNF level. Okay, so we use the SAT solver to obtain this group proof here. So that will consist of a sequence of clauses ending in the empty clause, and then you can just add the proof where you add the negated assumption here to every clause. And that will give you a proof of the unit clause containing this output variable. Okay. Yeah. So in this manner, we obtain a proof of the Zeitling translation of our circuit under the assumption that this is indeed unsatisfiable. And then we can append the QRET refutation of our that we get from the QCDCL solver and get a QRET refutation of the original PCNF QBF. Okay, and this is this part is fairly easy, although it's given me a little bit of a headache, simply because some of the in my solvers or in some of the solvers we can generate Q resolution. Oh, do you have a question? Oh, 5 minutes. Okay, fine. Yeah. We can generate Q resolution refutations, but then just converting to a QRET refutation, I discovered a couple of weird corner cases and bugs that can occur. So I've only done this so far for a fairly simple QCDCL solver, and I've yet to do it for Qt, where I would like to have this implemented actually. Okay, so what remains to do is fixing these bugs in the resolution tracing to make sure that we can actually get the QRET traces. In the current implementation, we also need a kind of a mapping between the gates of the circuit and the variables in the Zeitling translation, because we need to introduce these clauses in the Zeitling translation according to a topological ordering. Now I think we can just get rid of that simply by always making sure that the solver introduces or prints the clauses coming from Zeitling transformation according to some topological ordering. I suspect that may be the case anyway. I haven't really gotten around to trying this, but maybe this is not necessary, and that would simplify things and actually make the proof checking and proof construction independent of independent of the solver internals. One thing that we haven't looked into at all is how to do that for true formulas. As usual, there's this weird asymmetry in PCNF, where it's at least formally not clear how to do that for true PCNF. And finally, and that's a related issue, I think it would be nice to have a proof format for Freenet's normal form QBF. And I'm not sure what that should be. Okay, so that's it. Thank you very much.
Very much. Are there questions? Olaf?
Why can't you do cube refutations? Wouldn't it?
Well, okay. So we have these cubes. What do we need to relate that to the CNF? We have to prove that they are implied by the CNF, right? But then in the end, can we? So QRET would. So if we wanted a QRET proof, what would that have to look like now? If we would that be a QRET refutation of the negated cubes in that case? Possibly, yeah. Maybe that's all that needs to be done here.
Yeah, or maybe you could think of a dual version of QRET, where you operate on the cubes.
I mean, in that case, I think that should work.
Yeah, I mean, this would not even require a syntactic change, but you just have it in your mind that you're now talking about cubes and not about clauses. Yeah, like we have it in resolution. Yeah.
But then the original formula is still in CNF, right? Isn't that?
Yeah, the original formula is still
Okay.
CNF. Yes, yes.
Okay. Yeah. Yeah, that's something we should figure out in the coming days.
And the second question, if I may, so the first point you mentioned, Q resolution to QRAT. So what's the issue there?
Well, there's no formal issue. It's just that sometimes you simplify the input a little bit. If you have, for instance, you have a unit clause, then that gets removed from the negated literal gets removed from input clauses that come afterwards. And so you need to make sure that these steps are traced as resolution steps. So it's nothing, there's nothing interesting going on conceptually. It's just some corner cases.
Yeah, this is what is also an issue in SAT. So this is also transferred to QBF. And I think the SAT people worked a lot on getting rid of these things. And we also need to look at this. But these are mainly implementation details. Mina?
Yeah, so why did you mention specifically Q resolution? Do your CDCL solver runs always give Q resolution proofs?
They give Q resolution proofs, yeah, but there's nothing, I guess nothing specific.
No, they never give long distance.
Okay. Good point. This solver generates Q resolution proofs. But you could do it for long distance as well, right? There's a.
So if it generates only Q resolution proofs and it's still complete, is it?
Oh yeah, yeah.
It's level ordered?
No.
Oh, it's not level.
No, it's not level ordered. No.
Any other questions? Yeah, maybe another remark, but we really should talk. Equivalent substitution could be also be a technique that might work in this context. It's very similar, but a bit different and quite powerful.
Right, yeah. Mm-hmm.
Okay, good. Then thank you very much again. Yeah, and our next speaker is Mina, and she will talk about runtime versus extracted proof size. Please.
Hello, everybody. I want to talk about this work about runtime of a QCDCL solver versus the extracted proof size. And this is joint work with Olaf and Benjamin. It was presented at AAAI earlier this year. Sort of support credits here. So, okay, I have some more very introductory slides, which I will go over relatively fast and get to the real stuff. But just a little bit to give the context, because we are contrasting what happens with SAT versus what happens with QBF in this case. So with satisfiability, I mean, of course, satisfiability is important and it's interesting, and we are looking for efficient solver algorithms. The dominant paradigm there is CDCL, which is hugely successful. And where CDCL stumbles, if at all, is on random and unstructured instances or on handcrafted adversarial instances. On practical instances, CDCL does very, very well. So how do we understand exactly the limitations? Where does a CDCL solver actually take a long time? The main tool we have is that from the solver run, you extract a proof of unsatisfiability of the formula. In some sense, the trace of the algorithm itself is a proof, but you can convert it to a more formal proof. And then that proof, if you're extracting a proof in a particular format, if you can now show that in a specific format there are no short proofs, then you know that the trace must also be long. So this is where proof complexity comes in. Right? So here we're saying that from a typical solver, from the trace of the solver, you can extract a formal proof. The formal proof is easy to verify, and the format in which proofs are extracted from CDCL style solvers are in the format of resolution. So we have this is something which we have known for a long time, from 2004, that traces of these solvers naturally yield proofs in the format resolution. But of course, there can be more sophisticated formats that we would use. But already, I mean, resolution, the proof is easy to verify, and if we are able to give lower bounds. So this is my next slide. Yeah, this is where proof complexity enters. To understand the limitations of the SAT solver, what we want to do is we want to fix this format, show that in this format there is a correspondence between this proof format and the solver, and then one of these two things: either we search for short proofs, which is what the solver is doing, or independent of the solver, we sit as mathematicians and show that there are no short proofs, and then that means that the solver algorithm is going to take a long time. And what we do know in the context of CDCL solvers for SAT is that whenever you have a lower bound on resolution proof size, it must mean that every CDCL style SAT solver is going to take a long time. This correspondence has been known. So of course, one could also ask the converse question. So we know that when there are no short proofs, the CDCL algorithms are slow. But could it be that there are short proofs and still the CDCL algorithm is slow? And this we know in general is not the case. This result from 2011 and 2002 sets of papers, they showed that whenever there is a short resolution proof, indeed there are some non-deterministic choices that the CDCL solver can make, and then it can quickly zoom in and answer this question. So there is, in some sense, there is an exact equivalence between the size of resolution proofs and the length of CDCL solver traces. But of course, this non-determinism here is important. So if there is a short proof, then there is a choice of certain decisions to be made in the algorithm, under which the algorithm will run fast. But of course, real world implementations are going to be deterministic. They will use some heuristics. And for practical determinizations, in fact, the answer is it is possible to have short proofs, but all CDCL runs are following that determinization are slow. This was proved by Mark Winnels a few years ago. An explicit formula with a short resolution proof. But if you use the variable score index decaying score, then you would require exponential time. So now we want to look at this correspondence and see what happens when we are dealing with QBFs. And of course, by now we all know that QBFs are interesting and worth looking at. This is the format we're going to look at, and I'm going to stick to PCNF, notwithstanding whatever Friedrich says. There's this two-player game with which you can interpret QBFs, and the winning strategies for the players in this evaluation game correspond to Skolem functions or Herbrand functions. So now we can In the case of SAT, we could think of the solver as trying to find an assignment. It was not trying to find a refutation. If it failed to find an assignment, then it got a refutation. In the case of QBF, the solver is actually trying to find which of the two winners has a winning strategy, which of the two players has a winning strategy. Whichever of them has such a strategy, it would like to actually construct that. Okay, so we can ask this kind of question again in this world. So in the case of satisfiability, we said the solvers need to log proofs, and then those proofs can be checked, and that increases our trust in the algorithm. So with the QBF solver, can an answer be trusted? Well, we would want the solver to write down the Skolem function, or we would want it to write down the Herbrand function, depending on what output it gives. And then we have to verify that whatever function has been written down, is it indeed a Skolem function? Is it indeed a Herbrand function? So we even need to specify how the strategy is going to be written down, because now there's no asymmetry between the yes and the no cases. Both cases seem equally hard. Writing down this function is not necessarily going to have a compact form. So we would like to extract these proofs of truth or falsity in some format where actually there is a smaller representation, and still that small representation is easy to verify. So an explicit description of the function may not necessarily be the best way to go. So now we can ask for something very similar to what happens in the case of satisfiability. From CDCL style solvers which are handling QBFs, from traces we can extract proofs of falsity in this format, which builds on resolution. So this is Q resolution, typically with long distance as well. From QCDCL solver traces which detect that the formula is true, we can produce proofs of truth which are represented in the Q consensus with long distance proof system. So if you don't already know what these proof systems are, I'm not going to get into the details of it in this talk. There are these formats in which we can write down these proofs and extract them directly from the solver traces. So what this tells us is that for some formula, if I can show that there is no short proof in long distance Q resolution, a formula which is false, but there is no short proof in this format, then obviously the solver is going to take a long time. If for a true formula, if there is no short proof in this format, then again the solver is going to take a long time. So a lower bound on the resolution proof size again implies a lower bound on the solver runtime. Okay? And this is the analog of the Beam-Kautz-Sabharwal result for resolution. So there we saw that there is also a converse if we allow non-deterministic choices. So we want to ask the same question here. Is there a converse? But okay, maybe before we get to the converse, I should also say that this analog, that proof size lower bounds implies runtime lower bounds, it does hold for many different styles of QCDCL algorithms. So there are again these, the extracted refutation format, if you're looking at false QBFs, depending on the type of parameters that you would set in the QCDCL solver, the format of the proof would be long distance QRes or only QRes or quantified universal QURes and so on. So these are the three major styles which we did consider in our paper, because for these three styles, it was already shown by Olaf and Benjamin last year. Last year is the journal version. It was shown 3-4 years ago that there is this correspondence from solver runs to proof formats. So for these three types of QCDCL style algorithms, we do know that proof size lower bounds imply runtime lower bounds. And exactly as was asked in the case of propositional satisfiability, we could ask the converse. So in the case of propositional satisfiability, this question was answered, as I said, in 2011, that whenever there is a short proof, there is some non-deterministic choice which leads to a fast solver trace, a fast solver run. Is this also true for QBFs? Well, it turns out that for QBFs, the converse is definitely not true. This was again shown by Olaf and Benjamin in their earlier work. There are formulas which have very short and compact long distance Q resolution proofs, but the QCDCL solver based on this system, the type that I called MLD, it provably requires exponential time. So this was a bit surprising because we would expect that something like this should carry over. Is it just happening because there is this asymmetry between the yes and the no instances of SAT, but there is no such asymmetry in the case of QBFs? This was not completely clear. Why? So why exactly is this happening? This is the starting point for our work, that we wanted to understand this. Of the three QCDCL systems that I mentioned, this is the most powerful proof format, long distance Q resolution. So here we have short proofs, and the solver is still taking a long time. Why does this happen? This is what we want to explain. So one possibility could be that, well, there are short proofs in long distance queue resolution, but these short proofs are not the kind of proofs that a QCDCL solver could ever detect. So there's this entire family of all possible proofs of a formula. And then within that, there is a smaller subset of proofs which the kind of solver that we are looking at can actually construct. And it could be that the short proofs are not lying in that set at all. So really speaking, so is this the source of why that implication on top breaks down? No? That short proofs are not extractable by QCDSL solvers. So therefore, this is the question that we want to ask. Are there formulas where the runtime is exponentially larger even than the size of the extracted proof? I mean, could this happen, that the solver runs for a very long time and finally produces a tiny proof? This would sound more bizarre. Or perhaps could it be that there are formulas where the solver requires a long time and maybe it even produces a long proof, but there are short extractable proofs. It's just this particular run has not extracted it. So these were the kind of questions we were looking at for where the QCDCL solver is actually stumbling, why it's taking so long. And what we show is, okay, so what is here right now is what is already known, that if you look at the runtime of a QCDCL solver, the extracted proof is going to be smaller than that because you can extract it from the trace. And if you look at the shortest proof, in fact, maybe I should have stuck in one more category here, shortest extractable proof. This was the proof which was actually extracted by the solver, but I could look at the shortest extractable proof and the shortest proof, and these are ordered in this way. So as I mentioned, what was already known is that there is an exponential gap between shortest proof and solver runtime. And what I mean by an exponential gap is this, that there are formulas which have formula families indexed by n, polynomial in n variables, polynomial in n clauses, a very small quadratic size proof, and runtime exponential. So what we showed is that not only that, in fact, even this gap is exponential. So there are formulas for which the QCDCL solver is taking exponential time, and that same solver on that run produces a proof which is only polynomially large. So this is the new result that we show, and what this tells us essentially is that the slowness of the solver is because of the process of proof search. It's not because the proof itself is long. So until this point, most of the results that we had were either upper bounds for solvers or lower bounds. And the upper bounds for solvers would be that you just show a sequence of traces, sequence of trails in the QCDCL solver, which quickly zeroes in on a decision about whether the formula is true or false. And to show a lower bound, to show that some formula is hard for a QCDCL algorithm, typically we would give lower bounds here. So the lower bounds were the strongest possible and the upper bounds were the weakest possible in some sense. So this distinction that you can actually give lower bounds on the algorithm even when there are short proofs extracted by the algorithm, this is something new that we found. And this kind of separation holds in all the three models that I mentioned earlier. So just to very briefly, before I move on to a little bit more detail, to briefly emphasize what we're saying. In our examples, we are saying that there are short proofs, the algorithm actually finds the proofs, and the algorithm just takes too long to find them. This is the slide I should quickly run. So now, in order to understand, I would like to explain briefly how we got to the stage of constructing formulas which where finding a proof is very hard. Okay, so for this, I need to very briefly run through how a QCDCL solver works. Okay, so QCDCL, of course, it's taking CDCL, which runs on propositional formulas, and lifting it to QCDCL. So here's how CDCL works for SAT solvers. You repeatedly do unit propagation, or as we heard earlier in the school, Boolean constraint propagation. You set variables to satisfy unit clauses. If there are no more such variables, then you choose an unset variable, decide a value for it, set it, again do unit propagation. If some clause is falsified, then that's a conflict, and from that conflict you analyze it, you try to learn some new constraint which was not already there in your system. The constraint is typically represented as a clause, you add that clause to your clause set, and then you back jump to a suitable level, chronological, non-chronological, whatever. You back jump to a suitable level so that now when you resume, you will follow a different path because you have learned something new. So you will not necessarily do the same thing. You will definitely not do the same thing again. And if you reach a stage where all clauses are satisfied, then well and good, you report the current setting. So this is how CDCL works. It's a template because I mean, in each of these steps, there are so many things which are unspecified. How do you decide which variable to set? How do you decide what value to set it to? How do you decide what clause to learn from a conflict and so on? So it's a template. There is all this inherent non-determinism, and to implement it, of course, you will instantiate all these things. But the point is that resolution captures any algorithm which fits this template. So that's something very powerful. So now if I want to go over to QBFs, what's going to change in this template? So let's go step by step. Unit propagation. Instead of just setting variables to satisfy unit clauses, we will change the definition of what is unit. A clause is unit if it has only one existential variable and all the other universal variables are in some sense coming after it in the quantifier prefix. So then if the existential player has any hope of winning, it has to set that existential variable to true. So let's call these pseudo unit clauses. Existential variable in a pseudo unit clause has to be set. So the nature of unit propagation changes, but it's in spirit it's the same thing. Then you would again make decisions as before, choose an unset variable and assign it. A conflict could happen if some clause is falsified. If a conflict happens, you analyze it, you learn something new, back jump to a suitable level. If all clauses are satisfied, then in the previous case, when we were dealing with SAT, we said, oh, okay, we're done. We found that the formula is satisfiable. But here, that's not the case. Even if all clauses are satisfied, that still doesn't mean that the formula is true. But that does mean that here is something which is useful as far as constructing a Skolem function is concerned, as far as existential players runs are concerned. So we should be able to analyze this and learn something from this as well. So analyze why all the clauses are satisfied. From that, we will learn a new term, a new cube, and we will add it to the term set. So if I start with PCNF, initially I had no terms at all, but even then along the way, terms will get added, and then you would back jump to a suitable level. But now that we have added term sets, it may also happen that satisfaction happens because some term is satisfied. Again, we will analyze why, add something to the term set. So this means that at intermediate stages, we no longer have only CNF inside. We have some clauses, a conjunction of clauses, we have some terms. So that's why I also need to change something here about unit propagation. What are all these terms doing that are floating around? There will be unit propagation because of terms as well. So in a term, again, I will call some terms pseudo unit. If they have just one universal variable and all the other existentials come after that, then that universal should be falsified by the universal player if the universal player hopes to falsify the overall thing. So again, this universal variable can be propagated under such a setting. And the propagation will be to falsify the term. So basically, it's following the same template as CDCL with some modifications and some essential changes because there is no there is a symmetric situation between true and false for QBFs. So basically what is happening is that in this algorithm, we are following the perspective of an existential player. We are constructing a trail of propagated and decided literals. If a clause is falsified, then you learn that here is something that should be avoided in a Skolem function. If all clauses are satisfied or if some term is satisfied, then we learn something which we can aspire for, which is useful in a Skolem function. And at intermediate stages, the formula looks like this. So now it matters what are these terms that we are learning, how big are they, and that can also make a difference. So why are we learning terms? Well, term learning is essential for constructing verifications, for proving that a QBF is actually true. So of course, a practical QCDCL solver will have to learn terms. But if we just want to show that a QBF is false, in principle, term learning is not required at all. Without ever constructing a trail which leads to a learning of a term, we can still prove that false QBFs are actually false. If we add this term learning from a completely proof theoretic point of view, not necessarily in the solver, if we add term learning, it's not going to lengthen the shortest refutation because it's something that you can always choose to not do. But even on a false QBF, if you allow term learning, then a refutation could probably be shortened. And this is again what Friedrich talked about earlier, that if you have all those terms there, then you have all this additional information which can, even though finally the formula is false, it can drive you towards that end conclusion faster. So this proper separation, that term learning can provably shorten reputations. This was shown by Olaf and Thomas and Benjamin a couple of years ago. So how do we use this interaction between terms and clauses in proving our lower bound? So the main lower bound technique which we are using is something like this, that we start with some QBF, which is false, for which we already have a lower bound when there is no term learning. And like I just mentioned, there are formulas for which we do have such thing. And a formula for which if term learning is thrown in, then we know that there are short QCDCL traces. This is exactly what I mentioned in the previous Ichkai paper by Olaf, Thomas, and Benjamin. There are formulas like this, which term learning drastically shortens the refutation length. But the very fact that it drastically shortens the refutation length tells us, for one, there are short refutations. Okay, this part is taken care of. So there are not only short refutations, there are short proofs which are extractable because they are extracted by these solvers. Now we take this formula and we juxtapose it, combine it in some sense with another QBF which is true. So there's this QBFG, which is actually true. And let's rename all the variables so that they're completely disjoint from F. And we construct the juxtaposed QBF, which looks like this. It has all the quantifiers of F, then all the quantifiers of G, and then satisfy all the clauses of F and G. Well, in particular, you would have to satisfy QFF. You would have to, if this formula were to be true, then QFF would have to be true, and that is not the case. So this resulting formula is definitely false. And the question is, how are we going to show that this formula is false? Intuitively, it should be completely clear to us that in trying to prove that this formula is false, you cannot really use any information in G. No? The G part is true. It's not going to help you to prove the falseness of F. The G part is true. It is completely disjoint from F. How can it say anything about the falseness of F? So it can, a refutation of H cannot be helped by the presence of G. What we show is that it can be harmed by the presence of G. That's basically the message. So you can, here is the system about formula about which you want to prove something. Here is another formula which has nothing to do with this. By bringing it in, you cannot help proving things here, but you can actually make things worse. It's like adding noise which is muddling the scene. So how can it hinder the discovery of a refutation? How exactly can it harm this? There for me to use this. Yeah. So let's look at this formula. I want to try and refute this. If I think of a QCDCL solver which does not learn terms at all, then basically it has to refute the F part without learning terms. Our choice of F was that without term learning it is hard. So if we don't use term learning, we are anyway going to take a very long time. So then if we are hoping to refute H quickly, we would have to learn terms. But when do we learn a term? Only when all the clauses inside are satisfied. So that term that we learn will have all the variables of F as well as quite a few, well, not all, it will have many variables of F, but it will also have to have several variables of G. Enough variables to show that the G clauses were also satisfied. So now, I mean, we are saying not only has the term learned is long, and it is long in useless variables, in the variables of G, which had nothing to do with the falseness of H. So if I don't want the H variables, the G variables, I'm in trouble, because without term learning with F alone, I can't proceed. If I have to learn a term, the G variables will come in. I will have to remove all the variables from G before this term is going to become useful for refuting F. And now this is where we will choose G carefully. We will choose a form. Earlier I just said choose some true G, true formula G. Now I'm going to say choose a formula G that is hard to verify. So if it is hard to verify, it means, so when do we consider that QBF formula has been verified? We consider that the formula has been successfully refuted if we end up deriving the empty clause. We verify it if we end up deriving the empty term. So that's what I mean here when I say I have this term which has variables from G, and I have to remove all those variables through term resolution and empty out the term. I'm choosing a G which is hard to verify. So removing the variables of G from that learned term is going to take a very long time. So I have one trail which learns a term. It has all these useless G variables. Then I spend a huge amount of time getting rid of those useless variables. Then I can again say, okay, now let me get back to refuting F. almost at every step in between, I end up having this huge exponential loop, which is just trying to do the work of refuting G. So there are many technical details and subtleties just to put all this together nicely, but essentially it all works through. It uses key ideas from these 3 papers and says that you put in a true formula which is hard to verify, and it can completely muddle up your discovery of what was a short refutation of the false part. Okay. So the term learning comes with this disadvantage, but if you remove the term learning, anyway your formula was hard to refute, so either way you're sunk. That's how the lower bound goes. And here I have a list of some of the formulas that we actually used for these lower bounds. So for the first, for the main system that we wanted to look at, MLD, the false formulas were these so-called equality formulas. There exists an X for all U, there exists a T. And if you look at what these clauses are saying, they're saying at least one T variable has to be false. But here, you know, either Ti is true or Xi is different from Ui. Essentially, these 2 clauses are saying that. And so the universal player would very smartly play every U to match the corresponding X. And that would, through these clauses, force the T's to be true, and then you cannot satisfy the last clause. So that's why it's called the equality formula, because the winning Herbrand function is set every Ui equal to Ti. It's a false formula. And the true G that we use is actually a version of equality, which is then negated so that it becomes false. And the version, you know, the three gadgets are applied successively to it. And this technique is exactly what was used in the earlier paper by Olaf and Benjamin to obtain their lower bounds. So maybe I won't even go through these details, but they're there in the earlier paper as well. For the other 2 systems, we had a false formula which was even simpler than equality, so we just called it the simplicity formulas, where it looks a bit like equality, but if you look at these first 2, they are like even simpler. They're saying, well, obviously you would have to set Ui to false. Ui is appearing in only one polarity. Any universal player worth his salt would set Ui to false, and then the Ti's would have to be true. And for these formulas, the true formula that you would juxtapose next to it to obtain a formula which is hard to refute are the same true formulas that we used earlier. In this case, we cannot use equality as the false formula here for a very specific reason, that for equality, the extracted proofs we know would have to be large, no matter what you do. So we want formulas where there are short proofs. It is possible to extract short proofs. So these are the 3 formulas that played a role in our lower bounds: the equality formulas, the simplicity formulas, and this reversion operation. Those 3 gadgets applied to equality. And with the techniques which were developed in the previous 3 papers, we put together carefully, and we were able to get the bounds that we wanted. So the sources of hardness I have. Is the hardness essentially coming from level order? So this was also something that I asked. Is the ordering, in our case, the ordering is crucial in showing the lower bounds. So I do not know how any analog of this would hold if we are using a different order. Term learning is an advantage, but it seems like in this setting it's a hindrance. Yeah, so here there's still some question about the order. Yeah. Okay, so this is my final slide. Just to repeat that in the propositional world, we know resolution and CDCL are exactly related. In the QBF world, QCDCL and various versions of Q resolution are not exactly related. That is the point of the thing. And the fact that they are not exactly related was known, but we are tightening the separation between the proof search problem and the decision problems. So in some sense, it's saying that it is not automatable in a much stronger way than what we believed before. Thank you.
Thank you very much. There's time for a few quick questions. Friedrich?
Did you write a generator and did you write a generator for these formulas as well and test if they are indeed hard for Qt?
No, I haven't written any code at any point. I haven't.
I see. Because I suspect that, you know, as you said, the lower bounds rely on the order, the decision ordering being according to prefix order, and we have multiple techniques that can relax the ordering. So I would suspect that QBF in principle should also be able to figure out that this
So
part.
with
Huh?
depth QBF, certainly there are very short proofs. Whether a solver actually detects them quickly, I don't know, and that I would know only by running them. But
Yeah.
there are short proofs. This is clear
Oh
because
yeah, sorry. Even the search. I mean, would it be able to?
I
It
would
might
think,
have a chance of finding them quickly.
I think it would.
Qt as well.
Yeah. Even in Qt, which is learning the dependencies as you go.
Yeah.
Even there, you would expect it to find it quick.
Yeah.
Because if you compute the dependency right in the beginning, for sure it will very quickly terminate.
Okay, so no generator yet, but maybe we can
Okay.
get one.
Yeah. Thanks.
Yeah, I have a quick question. For depth QBF, we introduced this concept of generalized axioms, where you can learn partial cubes and shorter clauses by using some other proof techniques, which maybe swap to another proof system. Did you consider that?
No, actually, I'm not aware of this.
Okay,
So I
then,
should take
yeah.
I should take the references from
Yeah,
you.
because I think this is a very essential technique in depth QBF version 6, and I would be very much interested in the interfaces between proof systems. So where you switch techniques, you have this also a bit when doing in-processing, but this is even more extreme because you can learn information from this switch. And
it's almost like a portfolio proof system.
Yeah, exactly. And this is really an interesting direction, I think. And this is
Yeah. So I did not know about this.
Yeah.
Okay.
Okay.
Yeah, thanks.
Okay. Then let's have lunch and hope to see you in the third session. Thank you.